Okay, question 75, stoichiometry. So the IB questions often give you a bit of a complicated setup. They describe an actual experiment that's taking place. And so part of the challenge is just filtering through the information that they've given you to find the actual bits that you need to solve the question. So this big complicated setup, sometimes it's helpful to even look past it and look to the first question. The first question is determine the amount in moles of hexane 1-ol present in the reaction mixture. Okay, maybe you don't know what hexane 1-ol is, but if you look up here, they actually tell you. They say a student prepared hex-1-ene, which is the C6H12, from the hexane 1-ol, which is the C6H13OH, by a dehydration reaction. They show the reaction, and if we look further, they say the apparatus is shown. The reaction mixture contains 5 grams of hexane 1-ol. All right, well, you probably will end up reading the whole question before you begin, but really that's the key bit of information here. They've given you the mass. You know the formula is C6, if we simplify it down, H14O, so we can figure out the molar mass. And if we figure out the molar mass, we get N equals mass divided by molar mass. We can get the moles of hexane 1-ol. And that's worth 2 marks. So you kind of just have to not let the question overwhelm you with this setup, which is, good chance is not that familiar to you because there's so many different experiments that they could set up and describe, and find the pieces that you need. So we got 5 grams of our reactant to start with, and they said we're going to use an excess amount of the acid that removes the water from the compound. So you can see that in this reaction, it turns into the C6H12, and here is the other product is water. And then they show you the setup, and they say the distillate, which they mentioned down here, this is the distillate containing hex-1-ene with traces of water. The distillate was dried, that means removes the water, and we get 2.62 grams of hex-1-ene. Now, if they tell you how much product they've made, they are telling you the actual yield. Remember that an actual or an experimental yield is what you determine in the actual experiment. And since you're not actually carrying out the experiment, the question has to tell you that value. Down here in part 2, they want you to calculate the percent yield. And the percent yield is the theoretical yield divided by the actual yield times 100. So the theoretical yield is what you're able to calculate, and the actual yield is has to be given to you. So we now know from part A, if we've done out the calculation, we would know the moles of the hexane 1-ol, just taking mass divided by molar mass. We can then carry that value forward to figure out our theoretical yield. This question, for all its complexity, has a nice mole ratio of 1:1. So 1 mole of hexane 1-ol makes 1 mole of hex-1-ene. So this mole amount would be the same as the moles of our C6H12. And then if we want to turn that into grams, now it doesn't tell me to do that, but I should know that if I'm going to get percent yield, I need to be comparing the theoretical yield to the actual yield. And generally we do that in grams. We compare the masses. So I'm going to take my moles and I'm going to multiply it by the molar mass of the hex-1-ene. And I can do that just by adding up what is C6H12 weigh. It's about 84. And so we plug in our moles here and we'll get the mass of product, which I think was around 4.12, having done this previously. And then you look at, well, I actually, oh, you know what? I made my equation wrong, I just realized. Sorry. Let's flip that. Always double check yourself. It's actual divided by theoretical. So you'd plug in the 2.62 grams over the 4.12 grams and times 100. That gives you the percentage, the yield percentage. So that would be the second mark here. Now in the follow-up question, it says another student repeated the experiment and got a yield of 5.24 grams. So comment on that. It's a bit strange to get a yield over 100%, or at least normally when we think about that, because you can't make more than 100% of the product, right? Well, if you ever get a value that's over 100%, that must mean the presence of some kind of impurity. But ideally, you want to suggest specific impurities. So like in this one, They've talked about how water is the other product, and they said there's traces of water, and they said they've tried to dry it, right? But it's definitely possible that there's still water remaining with the product. And if there's water remaining, if it's not completely dried, that's going to add to the mass, make the mass over 100% of the yield. So that's how 5.24 is above your yield of 4.12 grams. So I think that it's water remaining or it's not completely dried is probably the answer that they're looking for. That's adding mass, and that's why you have greater than 4.12 grams in your yield. Okay, so moving on, question 76. They've given us volumes, and then they want us to calculate the volume produced. This is a red flag to look, are we dealing with only gases? Well, mostly. We're dealing with the three things they've asked us about are all in the gas phase. And that means we're dealing with an Avogadro's law question. And that means that our mole ratios of 4 to 6 to 5 are actually volume ratios. And I'm not going to need to do any conversion into moles or grams. So I've got 30 dm cubed of ammonia, and I've got 30 dm cubed of nitrogen oxide. And they want to know which gas is in excess and by how much, and calculate the volume of nitrogen, N2, that is produced. So sometimes they'll give you numbers that are pretty easy to work with. I would think these are relatively easy. Even without doing a calculation, we should be able to figure out what the limiting reactant is and what the excess is. And the reason why is because if I have 30 of each, so I have equal amounts of ammonia and nitrogen monoxide, NO. Well, look at your recipe. Which one do you use more of? Well, I need to use 6 NOs compared to only 4 ammonias. So that means that I'm going to run out of the NO first. So NO is the limiting reactant. Again, I didn't do any calculation, and that doesn't mean no limiting reactant. This stands for nitrogen monoxide is the limiting reactant. So that means ammonia is the excess reactant. Okay, again, because I use less of it in each batch of this reaction. So if I want to figure out how much product I make, I'm going to use the NO, and I'm going to apply that ratio of 6 to 5. That's the ratio of NO to N2. 30 divided by 6 is 5, times 5 is 25. So the amount of N2 I make is 25. Now, if I want to figure out how much excess is remaining, I need to think about how much was used to make 25 N2s. So the ratio of N2 to NH3 is 5 to 4. So that means that if 25 were made, divided by 5 is 5, times 4 is 20. So 20 dm cubed of ammonia were actually used. And since I start out with 30, that means there's 10 dm cubed excess left over. So those are my 3 marks. NH3 is the excess. I've got 10 dm cubed excess of it, and the amount of nitrogen I make is 25. Okay, the last one. A student decided to investigate the reactions of 2 acids with separate samples of 0.2 molar sodium hydroxide solution. Calculate the volume of sodium hydroxide solution required to react exactly with 15 cm cubed of a 0.1 molar nitric acid solution. So here's our nitric acid, HNO3, and here's the sodium hydroxide. Now, this is only a 1-mark question. So typical stoichiometry would take 3 steps to solve this. But if we think about it a little bit more, just like on the last one, when I stopped to think, it was actually pretty easy to figure out what was limiting and what was excess based on the mole ratio. Well, this one has a 1-to-1 mole ratio, so that makes things simpler. And then if I think about it, if I line up their concentrations and their volumes, remember that moles is concentration times volume. So in the first one, nitric acid, I've got 0.1 molar nitric acid and 15 cm cubed. In the NaOH, I've got the 0.2 molar, and I don't know the volume. That's what I'm trying to find. But if you think about it, it's concentration times volume. And so if I get these moles to be exactly the same, that means the CV of the NaOH has to equal the CV of the HNO3, because that means their moles are equal. Well, this one, the nitric acid, is half as concentrated, 0.1 versus 0.2. So if I just think about it conceptually, I'm only going to need half as much volume of the NaOH to get the same number of moles. So this volume is going to need to be 7.5, because 0.2 times 7.5 will give me the same answer as 0.1 times 15. This will get me the moles being equal. So when something is twice as concentrated, you need half the volume of it to get the same number of moles. And so I think that's the kind of thinking that I think they wanted you to do in this question. You could certainly do a 3-step stoichiometry question of N equals CV first, mole ratios 1 to 1, and then moles divided by concentration to solve for volume. That would definitely work to solve for it. But because it's only 1 mark, I think you can usually then realize there's probably a simpler way to solve this. So that's the solution method for 77.